Today I will present our mini project on digital system 2, which is student safe walk path. This is our team. The leader is Nur Sakirina. The member are Yashila, Kuha and myself, Ovia. No, student safety is a major concern, especially when crossing roads on university or school campus. To address this issue, we have designed a digital logic-based traffic light system that ensure a well-timed and efficient pedestrian crossing. The main challenge we identified is the risk students face while crossing the road, whether on foot or by bicycle. Especially in low visibility condition, existing system may not provide clear and timely signals, leading to confusion and potential accidents. This is our main objective for this project. Develop a student-safe walk-path light system using JK flip-flops. Design and implement all four states of the traffic light system to ensure proper pedestrian control. Last, display traffic light state using the DE board and allow control via a push button. To achieve these objectives, our work involves several key steps. Designing the digital system, including state diagrams and truth table with transition tables, simplify Boolean expression using Karnaugh maps, which is K maps, implementing our system in quadrants 2 using JK flip-flop and logic gates for circular operations, and simulating and testing the system to ensure
Hello, I'm Nur
accurate
Sakrina, the
timing
group
and smooth
leader, and
operation
I'm going to talk
of
about how we
pedestrian
get all
signals.
the state diagram, transition table, K-map to create the circuit for our traffic light project. First, we create a situation of having 5 lights, 3 for the vehicles and 2 for the students. The 3 lights for vehicles would be green, yellow, and red. For the student, we only have green and red. And as you can see, the very first state shows 10001. This state represents the one for the red light for vehicles and one for green light. These two will be on high, which will make the light appear. And on the second state, we have 10000, where only the red light for vehicles will be on high. And the third state, we have the green light for vehicles and red light for student on high. And the very last state, the Y for the yellow light for vehicles and red light for students will be on high and it will loop. Okay. The reason for having this second state of only red on high for vehicles is because before this we had a yellow light for student, but it seems too complicated of having 6 bits because now we already have 5 bits. If we add another one, it will be more complex and harder to solve. That's why we only go with the 5 bit, and it caused us to have this one states where the red light for vehicles will be on high. And from this JK code, we created all this K-map where for J4, the J4 will go to Q2 bar, the K4 will go to Q1 bar and Q0 bar, J3 will go to Q2 bar, K3 will go to VCC, J2 will go to Q1 bar and Q0 bar, K2 will go to VCC as well, J1 will go to Q1 bar and Q0 bar, K1 will go to Q bar, J0 will go to Q2 bar and Q1, and K0 will go to VCC. And this is the design and implementation. From the design, we can see that we have 5 JK flip-flop here for the 5 bit. And these are the output and the clock that we have assigned for it. And these are the input and output that we have assigned for this traffic light. We had a push button where we can as an input where the state will change every time we press on it. For example, for the first time we press on it, there will be 10001 state and so on. And here an output was connected to clock, and pin AE22 was designed to LED green on outside the e-board to make sure the clock is functioning well. LED green will blink at 50 Hz on the e-board as a sign that the clock is functioning. It means that it will also blink with other states when it appear together. That's it. Thank you.
Sila Anapampanjivan. The I will be explaining about the result of our student safe walk path project. The result for the two-way traffic light system was successfully executed on the Altera DE2 board. We were able to get all the state of the traffic light for vehicle crossing and student walking path on the DE2 board. At the initial state, the DE2 board showed some of the outputs altogether, which we thought it was an error, but later, the third time we pressed the push button, the DE2 board showed all the required traffic light state with no flaws at all. When we started the research about this initial condition occurred, we were able to learn that there are several issues that could lead to this initial condition. The most possible and suitable reason that we found was the glitches and delays in the logic circuits. We learned that if our design includes combinational logics such as AND gate, OR gate, or NOT gates to control the inputs of the flip-flops, there might have been a propagation delay or glitches at the beginning of the simulation. These delays might have caused incorrect or undefined states in the flip-flops at first, which was resolved as the simulation progressed. These reasons strongly resonate with our circuit design because we really used combinational logic gates to control the input of the flip-flops. Okay, and then these are the this table shows the states of the two-way traffic light that mainly focus on student walk path. The state that should show on the DE2 board simulation, which is 10001, 10000, 00110, 01010. Okay, okay. If we see here, this is where we assign the pins, the LED lights outputs on the DE board. We have about 6 outputs, and we have used push button to our project for our project. Okay, first of all, this is our clock. We used a clock output so that we know that our clock is functioning well. And then this is green 1 for vehicle, green 2 is for walk, red 1 is for vehicle, yellow 1 is for vehicle also, and red 2 is for walking path. Okay. Okay, this picture is showing the initial state that has propagational delay. At the start of the program, we can only see the clock output on high, and then as we press the push button, we can see the output that is shown on the DE2 board is an undefined state, which is 10011. If we look back at our state table, we don't have 10011 as our state. We only have 10001 as our first state. So this is definitely a undefined state. Okay, this undefined output is stating that vehicles will stop because traffic light rate is in high condition at LED rate 0, and at the same time the green light for vehicles also on, also vehicles on LED green 5 is also high. Additionally, there is a third output showing high on LED red for walk for student safe walk path. As we have stated before, this undefined state occurs at the starting of the system because there might be glitches and delays on the logic circuit used to control the 5-bit JK flip-flop inputs. The second time the push button was pressed, the red light for vehicle, the yellow light for vehicle, and the red light for student safe walk path spontaneously lit up, also giving an undefined output which is 11010, an undefined state. This undefined condition resolved at the third time the clock blinked at LED green 0. Okay. Picture showing the first state of the two-way traffic light system that mainly focus on student safe walk path. Here we are seeing the first traffic light state output of the two-way traffic light, which is 10001. After we press the push button for the third time, LED red 1 for vehicle and LED green 2 for student safe walk path is on high condition, indicating that when vehicle stops, student can cross the road safely. The green output showing high on the further right is the output for clock. So we were able to get the first state of our traffic light system at the third push of the push button after the propagation delays on the first and second clock. Next, picture showing the output of the second state of the two-way traffic light that mainly focus on student safe walk path. At the fourth clock, or at the fourth press of the push button, the second state of the two-way traffic light showed up on the Altera DE2 port, which is 1000. Only the red one light at LED R0 for vehicle will lit up at this state, indicating the vehicles should stop. Next, for our third state, picture shows the third state of the two-way traffic light system that mainly focus on student safe walk path. As we can see, the third state of the two-way traffic light system that ensuring students safe walk path is successfully obtained from the design build, which is 00110. In this state, it shows high for LED red 2 and high for LED green 1, indicating that LED red 2 is for walk, LED green 1 is for vehicle, indicating that when red light lit up on the student safe walk path, people will stop walking while the vehicles will start moving. Because green light lit up for vehicles, this state of the traffic light was obtained on the fifth time the push button was pressed. Lastly, picture showing the fourth state of the two-way traffic light system. The output of the fourth state two-way traffic light system that mainly focuses on student safe walk path was successfully executed on Altera DE2 board, which is 01010. We can see that the LED yellow 1 for vehicle and LED red 2, we can red 2 for student walk path is in high condition. This shows that the yellow light for vehicle indicate that red light for vehicle is going to lit up soon, while green light for student walk path is also going to lit up. If we see closely, this indicates the state 1 of our two-way traffic light, which is 10001, where LED red 1 for vehicle will lit up and LED green 2 for student walk path will also lit up at the same time, enabling students to cross the road while the vehicle stops. This process is called looping. The system loops back to state 1 after completing the cycle, ensuring that process repeats. This continuous cycle allows the system to manage the lights in a way that gives priority to both vehicle movement and student safety while crossing in an alternating manner. The looping process is a two-way traffic light system is crucial for ensuring a smooth and predictable flow of traffic while keeping students walk paths safely in focus. Next, I'll be I'll be discussing about the discussion of our overall project. When we completed our design on Cortex 2 software, the circuit compilation process was successful and we were able to program the circuit design on the Altera DE2 board and able to get all the traffic light states. However, our outputs were racing continuously, making it difficult to notice the traffic light states on the DE2 board. After some thorough observation on the outputs that showed up, we came to a realization that we didn't include the push button pin in the clock input. We identified that the missing push button output at the clock input is the reason the traffic light states were racing continuously. Measures taken to troubleshoot these issues are troubleshooting continuous racing of traffic light states due to missing push button input. First, we recognize the symptom, which is the lights were racing continuously, making it impossible to observe the intended sequence of the traffic light. So the second thing we did is verify the missing push button in the circuit design on our Quarters 2 software. We noticed that the push button function was missing in our circuit. Third, we assign push button input into the circuit design. We assign the push button in the circuit design by assigning pin G26 in the clock input. Push button key 0 will be used on the D2 board to obtain state 1, 2, 3 and 4. And then fourth, lastly we recompile and program. After making the changes required on the circuit design, we recompile and design the design. The compilation was successful. We programmed the circuit design to Altera DE2 board and was able to get all the 4 states of the traffic light after pressing the push button key with no racing outputs. So the troubleshooting and testing of the program was successful. Contrary to our expectation, after troubleshooting and testing, we were able to get outputs according to our state diagram with no racing but with some propagation delays due to complex combinational circuit usage to control the 5-bit JK flip-flop inputs. These propagation delays occurs till the second clock or the second time we used the push button and showed undefined states. The propagation delay is the part where we face some challenges due to find the reason it happened and limitations to fix it due to the complexity of our circuit design. Lastly, we were able to achieve all our objective of our student safe walk path project, which is to build a student safe walk path traffic light system using JK flip-flop to get all 4 states of our student safe walk path traffic light system using JK flip-flop and to obtain the traffic light states on the E2 board using a push button. That's all. Thank you. இது தெரியுதா இல்லை இல்லை okay. First state, we get undefined state because of the usage of combinational circuits to control the inputs of our 5-bit JK flip-flop. In the second state also we get undefined states. At the third clock, we get our first state, which is the pedestrians can start walking, vehicles will stop, and at the second state the vehicle still will be in stopping position because the rate is showing high. And at the third state, vehicles can move and pedestrians will stop. At the fourth state, the yellow lit up for vehicles, and then the pedestrians will still be in stopping position, and then looping, which it goes to state 1 again. Thank you.
Hi everyone, my name is Kuha Lakshmi and I will be talking about the impact of the Student Safe Walk Path project on the community. The impact of our two-way traffic light project, it focuses on student safety and its impact on the community, and it can be broken down into 3 categories, which is family, individual and national perspective. Speaking of families, it will reduce their anxiety and increase their peace of mind. Parents will experience a significant reduction in anxiety concerning their children's safety when crossing busy roads near schools. The predictable and automated traffic light system, it provides a sense of security knowing that a structured and safe student crossing environment is in place. Additionally, with a clear and easy to understand traffic light system, parents can feel more comfortable allowing their children to walk or bike to school independently. It, it promotes student physical activity and self-reliance. As an individual, for example, students will have improved sense of safety and security. Students will feel more confident and secure when crossing roads, knowing that the traffic light system is designed to enable them cross roads safely. Moreover, there will be reduced risk of accidents and injuries for students and also vehicle drivers. Finally, for the country, there will be reduction in traffic-related injuries and fatalities by prioritizing student safety in school zones. This project contributes to a national effort to reduce traffic-related injuries and fatalities, particularly among students. Furthermore, this project also can contribute improved public health and well-being by creating a safer pedestrian environment, encouraging active transportation such as walking and cycling, which contributes to improved public health and well-being. Moreover, the Student Safe Walk Paths project also can pave the way for improved school safety practices. Successful implementation of this project can serve as a model for other schools and communities across the country, promoting a widespread adoption of effective student safety measures. In conclusion, for our future works, while this two-way student safe walk path traffic light system mini project has successfully achieved its course objectives, which is to build a student safe walk path traffic light system using JK flip-flop to get all the four states of the student safe walk path traffic light system and to obtain the traffic light states on DE2 board using a push button. Further development is necessary to realize its full potential. Specifically, the current circuit design's complexity stemming from the use of a 5-bit JK flip-flop configuration needs to be addressed. So simplifying the design to a 4-bit JK flip-flop would significantly reduce the number of connections, and it will be easier to troubleshoot and enable more simpler design using 4-bit keymaps. The 5-bit implementation necessitated the use of numerous combinational circuits, which introduced propagation delays in our results. Optimizing the design in this manner will improve the system reliability and performance. So in the future, we plan to use timer for our traffic light system and a more simpler circuit design. We can see that we can obtain a clear vision of the future development of our student safe walk path, and below is the transition table that we managed to draft for the future development of our project. This is the transition table for our future circuit design. And for the future development, we have designed a transition table using a 4-bit JK flip-flop configuration. This table maintains the 5 outputs: red, yellow, green, red and green for vehicle and also walk, which is necessary to replicate the traffic light states of our current student safe walk path system. To simplify the circuit design, we will plot K-map for each of the 5 outputs, resulting in 5 simplified combinational circuits. These circuits will then be connected to the corresponding outputs of the JK flip-flop, and this approach is expected to yield more efficient and less complex circuit, overcoming the propagation delays observed in our present project. In conclusion, this project has laid the groundwork for timed and simple traffic light design. Thank you.